really there are 6 inverse trigonometric functions, but you can sort of just write off 3 of them right away because their derivatives are just the negatives of the. You can write off the co-functions because their derivatives are just the negatives of the regular inverse trigonometric functions. Okay, so the 3 regular, meaning like sort of like non-co-function inverse trigonometric functions, those were, as a reminder, arcsine. You might also see sine with a little inverse notation on the corner. It's not an exponent of -1. It's not like the reciprocal. That exponent looking thing. If you ever see that. Let's just say arcsine of u, or yeah. So this little -1 is not an inverse. Sorry, no. It's not an exponent. Meaning it's not 1 over the sine or anything like that. It literally means the inverse of sine, which is a completely different function altogether. So don't just take 1 over the sine of u and say, okay, well that's the arcsine. Okay, so the derivative of this is, you can say that there's u prime on top, or you can say that there's u prime multiplied at the end. It doesn't matter. But this is the sort of general formula. If what u is happens to just be an x, then the derivative of x is just 1, and so you'll just have a 1 on the top. But if it's anything more complicated, you actually have to like sort of figure out what u is and what u prime is, and put that on the top instead. Okay, so other than that, there's u prime on top, and on the bottom, it's marked by a square root, and underneath the square root, there's going to be a 1 minus u squared. In that order specifically, not u squared minus 1, but 1 minus u squared. And I'm just going to sort of write that in. All right, so just remember that that is sort of part of what differentiates this function from the others. Having the constant squared first minus the variable squared. The second of these is, we say that that's arctan. Or, the inverse tangent. And the derivative of that is marked by having no square root. But more importantly, it's marked by the addition of both of these, of 1 and u squared. Or u squared and 1. If it's addition, the order doesn't matter. It'll be important to sort of recognize this because we're going to talk about the functions that have these as their antiderivatives. We're going to integrate into these inverse trigonometric functions today. Right, so it's just the constant squared plus a variable squared, and just sort of remember, keep that in mind for today. And the last one is arcsecant. the derivative of which is easily the weirdest of the three, because like the others, it starts off with a u prime on top, a 1 on top if x is just what happens to be inside, but the actual u prime otherwise. But it's the weirdest because it's marked by an absolute value bar on the outside of a square root. So it's easily like the most unique of these three. And underneath the square root, there is specifically a u squared minus 1 in that order. Not 1 minus u squared like the arc sign, but u squared minus 1. Okay. And so that's going to be some sort of variable term squared minus some sort of constant squared. Right. In these sort of derivatives that you learned on Thursday, of course, the constant is just 1, but maybe today we'll see some cases where that is where it's something different. So that's basically just that's what we learned on Thursday. Oh, and like a refresher of like what an inverse trigonometric function actually is. Okay. So the things that we're going to do today are we're going to integrate something into an inverse trigonometric function. So basically, we're going to take something that looks like the derivatives that you learned on Thursday, like those derivatives with the like these derivatives right here. You're gonna take something that starts off looking like this and integrate it so that it becomes an inverse trigonometric function like arcsine or arctan or arcsecant. Basically just sort of reversing the process of whatever we learned on Thursday. And we're also going to review completing the square, which you definitely probably learned in algebra, and maybe had to use in pre-cal. And last, we don't really have to do that last one. We sort of did that on the first day. Right. So although there are 6 inverse trigonometric functions, we really only have to know those 3 that I wrote down there. Because for the cofunctions, the derivatives of the inverse trigonometric cofunctions are just the negatives of the regular ones. So, for example, the derivative of arc cosine, the derivative of that will simply be the negative of the derivative of arcsine. Arc cotangent's derivative will be the negative of arctangent's derivative, and arc cosecant's derivative will be the negative of arcsecant's derivative. So you don't really have to know anything for those inverse trigonometric cofunctions. Right, so let's say you start off with 1 over the square root of 1 minus x squared. If you try to integrate that, well, you could, say either, you could either say it's arcsine, that is the derivative of arcsine. So if you try to integrate that, you could say that the antiderivative of the integral is arcsine, but you could also say it's negative arc cosine, but there would sort of be no need to. So it's not wrong, but don't force yourself to remember, 6 derivatives or antiderivatives when you can sort of get away with knowing only three. Okay, so these are the three antiderivatives. And you'll notice that they're really similar in form to the derivatives that you learned pretty recently on Thursday. Okay. There are some minute differences. I mean, I'm just going to end up highlighting the whole thing. Like, okay, it's all, every piece is important. But specifically, note that it's no longer necessarily 1 minus u squared or u squared minus 1 or 1 plus u squared anymore. It doesn't have to be 1 anymore. It can be any constant. And whatever appears there is going to be considered a constant squared. So sometimes, underneath the square root there, or, on the bottoms of any of these, you might see, 4 minus u squared, or 9 plus u squared, or u squared minus 25. Because it's always going to be some constant that you're going to call a squared. And it might not even necessarily be a perfect square. If you have, for example, if down here you have 3 minus u squared, then that simply means that a, the value of a, is a square root of 3. So it's not necessarily always going to be a perfect square. But it will be a perfect square a lot of the time. So there are a couple things to note that, first is that it's not necessarily 1 minus u squared, 1 plus u squared, or u squared minus 1. When you're dealing with antiderivatives, that constant can be anything. But do sort of, make a note of what the value of a is, because you'll see it incorporated into the actual, into what the antiderivative is right here. Actually, in several places that I'm going to, mark in green or whatever. Okay. And other than that, it's pretty standard. There is a little special thing about the arcsecant. Okay. So 3 things. The constant is not necessarily 1. For these antiderivatives. It can be 4, 9, 16, 25, 36, 49, 64, or even a number that isn't a perfect square. So do note what a squared is, and figure out the value of a. Because a appears in the antiderivative. So while you might be wondering, hey, how come these antiderivatives don't look exactly like the derivatives, that we learned on Thursday, there is a good reason for that. There would be a different way to conceive of this that makes it fit more in line with what you learned on Thursday. But but if you did that, the actual derivation of these antiderivatives would be a lot more difficult. And I'll actually show one of these to sort of show you guys like why it's less complicated to think of it this way, even if it's different than what you learned on Thursday. Okay, then last, let's see, arcsecant has, so for the antiderivative that becomes arcsecant, the arcsecant has the absolute value not here, it doesn't, but rather here. So while that is backwards to sort of how the derivative is, when you take the derivative that you get is going to have the absolute value bars. But when you integrate into arcsecant, the integral or the antiderivative has the absolute value bars. So while that is different, what is similar is in that in both times the arcsecant has the absolute value in your result. You're not going to start off with an absolute value bar, but it is going to be in your result, whether you're taking the antiderivative to create an arcsecant, or you're starting with an arcsecant and you're finding the derivative, the absolute value bar is going to be in your result. Now, what I'm about to do next, you don't have to write down. This is just sort of a justification for why these are written the way they are. Okay, so okay, so you do not have to write this down. But let's say you started, you wanted to take the integral of 1 over, let's say the square root of 9 minus x squared. Now that's not exactly like the derivative that you learned on Thursday, right? The derivative that you learned on Thursday would be like 1 minus x squared, not 9 minus x squared. So if you really wanted to force this into sort of fitting the form of what you learned on Thursday, this is what you would have to do. All right, let's try to make that into a 1. The way that we're going to do that is, and again, you don't have to write this down, but the way that we're going to do that is we're going to factor out a 9 from inside this square root. Because if you factor out a 9, that 9 is going to become a 1. Okay, so it's still under the square root, though. We're going to factor a 9 out of that, and so that's going to become 1 over, and if you factor out 9 out of x squared, what you're going to get is x squared over 9. Right, you can sort of imagine if you try to multiply that back, you get 9 minus x squared. But that's what you have so far. Okay, and since these are now broken up, right, the 9 and this sort of parenthetical phrase here, you can split those up. Square root of 9 and square root of 1 minus x squared over 9. I just split that up into 2 square roots, and that is 1/3. right? Square root of 9 is 3, so that's 1/3, and we're going to just take that 1/3 and throw it in the front. Doesn't really, you know, matter or nothing. You know, actually, what would probably be better is, let's write it like this. Let me just take that 1/3, instead of putting it in the front, I'm just going to put it on top, like make a little complex fraction. And just one more step before the integration can happen. X squared minus 9, I'm going to write that as x over 3, like all of x over 3, like in parentheses, being squared. Okay, so now we're ready for a u substitution. If u equals x over 3, right, the form that you know is, the square root of 1 minus u squared, so whatever is being squared is u. Like whatever variable term is being squared, there is u. Then that means that du is 1 over 3, because that's the derivative of this, dx. And, while from here you can proceed however you want, you can multiply both sides by 3 to isolate dx, like multiply both sides of this to isolate dx. Or you may recognize that you have 1/3 dx and simply replace that with du. It's, your call. So I feel like recognizing that you have 1/3 dx is sort of like the easier thing to do. So I will simply do it the other way. So what this means is that 3 du is dx. Okay. So after this u substitution, this is what it's going to look like. So x over 3 is replaced by u, so it's 1 minus u squared. And du is going to be replaced by, dx is going to be replaced by 3 du. And pretty clearly that, is going to... So you have the integral of 1 over square root of 1 minus u squared du, which is the arc sine of u plus c. So that's simply the arc sine of x over 3 plus c. Okay, so that's how you would do this if you sort of refused to learn, this, like in terms of identifying what A and U are. But if you did allow yourself to sort of, learn these, forms, then this is what you could do instead. You could simply say, okay, let's say we got the integral, let's say we got the same integral. Okay, well, this is supposed to be a squared. So if a squared is 9, then a is 3. If u squared is x squared, then, well, our u is clearly x. Following the sort of formula, I guess it's a formula. Following the formula from the last slide, you would simply get that this is the arc sine of u over a, so x, because that's our u this time, over 3, because we identified 3 as our a, since we had 9, and 9 is supposed to be a squared. There you go. So while you can do these integrals just from like remembering the derivatives from Thursday, in order to make them sort of fit the format of like those, you know, that you learned on Thursday, you know, it sort of involves factoring constants out of this denominator and some u substitution. Whereas if you simply remember these, it's just identifying, okay, what's u, what's a, you know, do I have the appropriate du or whatever, and then simply just like saying it's arcsine of u over a, or 1 over a arctangent of u over a, and so on. What is important to note is that in every situation, it's in every one of these, u over a is what's inside the function. But in addition to that, arctangent and arcsecant have an extra 1 over a in the front, whereas, you know, arcsine does not. Okay, so let's do a couple of these. This is not really conducive to, okay. Okay, so dx over the square root of 4 minus x squared, and let me just grab the others as well. Okay, well, I probably should have grabbed the letter that indicates it too. Alright, so these are 3 integrals. You can sort of tell by looking at them, they're probably going to each become like a different inverse trigonometric function. But in every situation, it would definitely be the best thing to, you know, identify what a is and identify what u is. All right, so this isn't too dissimilar from what we just did, this first one here, but here we've got a, first of all, there's a square root. And second, what's under the square root is a constant squared minus a variable squared. And that uniquely identifies this as becoming an arcsine. So it is going to be an arcsine. And arcsine doesn't have anything special in front of it. It just sort of starts off as arcsine. It's going to be the arcsine of u over a. So we'll just figure out what u is and what a is. Okay. And as they appear sort of there, they're not just straight up u and a, but they're u squared and a squared. So the constant is actually a squared. So 4 is a squared, meaning that a is 2. And u squared is, so the variable term squared is x squared, meaning that u is simply x. So if you're looking for the arcsine of u over a, well, that's going to be the arcsine of x over 2. And then a plus c because this is an antiderivative. That's it. For the second one, you'll notice there's no square root. There's almost nothing except that they're being added together on the bottom. A 2 plus 9x squared. which marks this as becoming an arctangent, because arctangent is the one where its derivative has the addition on the bottom, and so this is going to become an arctangent. So first, let's go ahead and identify what u squared and a squared are, and then what u and a are. This constant is actually a squared, so a squared is 2. So a is the square root of 2. Our variable square term is this 9x squared that's down here. And so if you take the square root of 9x squared, what is that going to be? Yeah, right? Yeah. You want to take the square root of the whole thing. So the square root of the 9 part is going to be 3, and the square root of the x squared part is going to be x. So u squared is 3x. No, u is 3x. Yeah. Okay, so this is so that's actually kind of important, because u is now no longer just a plain x like it was in a, or even just the example that I made up prior to this. So u is 3x. What that means is that du is going to be 3dx. So there might be some very minor u substitution involved here. Okay. So if du is 3dx, what that also means is, of course you could say, you could force there to be a 3 up here and a 1/3 outside. You can do it that way. But you can also take this du equals 3dx and make yourself a little equation. 1/3 du equals dx. Okay. And that's going to be necessary because u is something more complicated than simply x. It is 3x, which isn't much more complicated, but yeah. Okay. Okay, so because this u substitution is going to be necessary, I'm just going to rewrite this for a step. And so it turns out that 1/3, we don't really need that or anything to be in here. We can just move that to the outside. And other than that, we'll have what we want. We'll have du over 2 plus u squared. Okay, so the integral of that is going to be, there's still going to be that 1/3 from before. And the integral itself, the antiderivative itself, is going to be, this is an arctangent, so it's going to be 1 over a times the arctangent of u over a. So what was a? A was the square root of 2, right? So 1 over the square root of 2 times the arctangent of u over a. And you can write in, u over the square root of 2 and then change the u later. Which I guess I will. feel free to just skip this if you know what u is, which you do, but I generally don't like to skip too many steps, even though I could. So altogether, that's 1 over 3 square roots of 2 times the arctangent of 3x over the square root of 2 plus c. And honestly, it's probably best for you guys to see as much u substitution as you can. Because you can always generalize u substitution to like simpler cases, but it's hard to go the other way around. If you don't see u substitution, then it's hard to sort of. Okay. Then the last one. First one was an arcsine. Second one was an arctangent. This one looks different from either of them, so it is probably an arcsecant. And you can also tell because one, there's a square root. I mean, sure, arcsine has a square root, but this square root has the variable squared minus the constant squared, right? That is one thing that sort of identifies this as an arcsecant. And the second thing that identifies this as an arcsecant is that there's an extra variable on the outside of the square root on the bottom. And so we're looking for something that looks like this. We're looking for something that looks like the integral of du over u times the square root of u squared minus a squared. So kind of like that so far, not exactly. So first, let's, like the other times, let's identify what u and a are. Okay. So u squared is this 4x squared that's right here. And if you take the square root of that, well then u is going to be (2x). Right, that is the square root of 4x squared. And if a squared is 9, well then a is 3. Okay. So again, u is not simply x, it is 2x, meaning that we should probably make a note of what du is. So du is going to be 2 dx. And we can also say that 1/2 du is equal to dx. Right, so multiply both sides by 1/2 or divide both sides by 2, however you want to look at it. Okay, so let's substitute some of those things to maybe hopefully make this look a little better. Alright, so dx, right, is 1/2 du according to this. Let me just sort of separate these visually. Okay. So 1/2 du on top. And, it's not going to be a complex fraction for long. We're going to fix this. What should we do to this x? I don't really know what to do with this x, so I'm just going to write an x for now. I mean, I actually do know what to do with it, but let's just pretend. Okay, now 4x squared minus 9, that's the u squared minus a squared part. Now, let me just take this 1/2 that's right here, and instead of having it like a 1/2 like as a fraction on the top of this fraction, let me just, imagine having this in the front of the fraction. Like, imagine having it like 1/2. That's just going to give you a 2 on the bottom. So another way to think of it is that, by having this 1/2 up here, you're multiplying by 1/2, which is equivalent to dividing by 2. So a 1/2 on the top, you can put a 2 on the bottom instead. So you're simply going to have du on top over 2x u squared minus a squared. Also, I mean, you don't have to write a squared. You can just write that it's 9. It doesn't make a difference either way. But now, what we got on the bottom is a 2x, which you might recognize as being what u is. So this is u. So just by taking that 1/2 and moving it to the bottom, we've created du over u times the square root of u squared minus a squared, which is perfectly that that sort of integral that over here, right? The third one for arcsecant. So despite looking a little bit weird at first, it turns out to be exactly the integral that you learn the formula of. Okay, so this is 1/a times the arcsecant of the absolute value of u over a. So a was 3, so 1/3 times the arcsecant of the absolute value of u being 2x, so the absolute value of 2x, over a, which again is 3, plus c. So there you have it. So at worst, there's like a little bit of u substitution. Generally, in terms of just needing an extra constant or moving out a constant. Other than that, it's just sort of like identifying what a and u are, and then just throwing those into these here. Just leave that there for you guys need it. Yeah. All right. So completing this square is this is something that you would have learned in algebra when you were talking about like quadratics or polynomials. Probably when you were talking about like taking a quadratic function and like changing it to like the equation of a parabola and changing it to like vertex form, as opposed to standard form. If you guys even remember that, it's probably pretty far back. Yeah, 3 semesters at least. Okay. All right. So assuming that you start off with some sort of quadratic expression of the form x squared plus bx plus c. The way that you can complete the square is there's a single sort of magical number that you can add to this expression. And also, because you're going to add it to this expression, you're going to subtract the same number from the expression so that you don't change what the expression actually equals. So what I mean by that is you're going to have x squared plus bx, and there's just going to be a number that you're going to add here. However, because you don't want to change the expression, like right after, you're going to subtract the same number. Like you're going to add 2 and subtract 2, or add 9 and subtract 9. And so that's sort of the basis of completing the square. Now, what this number actually is, this number is always b over 2 squared. That's the number that you're going to add and subtract in order to complete the square. And if you do that, this is going to become x plus b over 2 all squared. And then just sort of like plus or minus some other number as a result of this part. Okay, probably better to see it not in terms of like b and all these hypothetical constants. All right, so for an example, let's just say we got x squared plus 10x minus 17 or something like that. Okay. So the value of b in this expression is 10. This is our b. So if b is 10, b over 2, just cut it in half, right, is 5. And b over 2 squared is 25. So 25 is sort of this number that we're wanting to add and then immediately subtract from sort of the middle of this expression. So just, I mean, you could remember b over 2 squared, but you could also just be like, take whatever b is, cut it in half, square it. That's what goes, in here, being added and subtracted. So this is going to be equal to x squared plus 10x, that's still there. But we're going to add and subtract, plus 25 minus 25, add and subtract 25, just sort of in the middle of this, and there is still that minus 17. Okay, so the reason that it has to be 25, or that it has to be whatever, single value that it is with the b over 2 squared, the reason that that has to be is because only then well, these three terms form what you would call a perfect square trinomial. And if it is a perfect square trinomial, it should be able to be condensed into a binomial squared. And that binomial is going to be x plus b over 2, whatever b over 2 was. And basically the number after you cut it in half, but before you square it. So for us, that was 5. You can also just, take for granted that this is a perfect square trinomial and then just try to factor it anyways. Look for two numbers that multiply to 25 but add up to positive 10. You'll find that it's plus 5 and plus 5, meaning that it's x plus 5 times x plus 5. Like, this factors into x plus 5 plus time. This factors into x plus 5 times x plus 5, or x plus 5 all squared. So you can, once you have this perfect square trinomial, factor it like any other trinomial and then end up with this binomial squared. Or you can remember that it's, that a perfect square trinomial is meant to condense into x plus b over 2 all squared, whichever way, it doesn't really matter. And then just this minus 25 and minus 17, you combine these at the end to just whatever constant forms. In this case, minus 42. But that square is completed. And this minus 42 is just sort of hanging out at the back. So the steps are basically first make sure that you're starting off with x squared, not like 3x squared or 4x squared or anything like that. Make sure it is starting off, exactly this way. But once you do that, identify b. Find b over 2 squared. Add and subtract b over 2 squared. And then condense the resulting perfect square trinomial. Into a squared, into x plus b over 2 all squared. In case you do have a constant in front of the x squared, let's say your trinomial starts off with like a 9x squared or something like that, then all you need to do in order to be able to do this is just factor that constant out. If you have like 3x squared plus a bunch of other things, just factor that 3 out. So that 3 is just sort of in the front end. In the inside will now be this sort of like x squared plus the whatever the x plus constant at the end. In rare cases that may happen. But yeah, if if the x squared has a coefficient, factor it out of the trinomial. All right, so this is sort of the mathematical justification of this thing. Start off with x squared plus bx plus c. You don't have to write this down. This is sort of what we just did. This is the second step. So you're adding and subtracting b over 2 squared, right? This sort of magic number. And then what happens is, well, you're able to condense those first three terms into this squared binomial, x plus b squared all squared. And then this part becomes like just a constant, Okay, so start with this. Shit. So the way that this is written, this doesn't exactly look like very much of anything that you've seen so far. Yeah, it doesn't really fit the form of any integrals or antiderivatives, that you've learned up at this point. But that doesn't mean it can't be done. Let's see what this looks like after we complete the square. Okay, so we're just going to focus on the denominator right now. X squared minus 4x plus 7. We're going to complete the square on that and see what this integral ends up looking like. So x squared minus 4x plus 7. So our b, looks like our b is negative 4. Yeah, make sure to make sure to be including whatever sign is there. If it's a subtraction, make sure that b is negative. If it's addition, make sure that b is positive. But b will be negative 4. Meaning that b over 2, just cutting that in half, is going to give us negative 2. And b over 2 squared is going to be, if we take negative 2 and we square it, that's going to be positive 4. So that is the number we're going to add and subtract. X squared minus 4x, and we're going to add and subtract this b over 2 squared number right now. Plus 4 minus 4, and then just that plus 7 that was there before. Okay, yeah, sure. So now these first three terms, including that 4 that we sort of added in there, that should form a perfect square trinomial, and it should factor or condense into x plus the b over 2 number. Now, that's the number after we cut it in half, but before we square it. So our little b over 2, that's negative 2, and make sure that, and that's why it's important to keep the sign, like recognize what the sign of b is, because that's going to affect what your b over 2 is. So we want to add this negative 2, basically meaning that we're going to have x minus 2 squared as the condensed form of this perfect square trinomial, formed by these first three terms. And then this minus 4 and plus 7, well, that's just plus 3. Okay, so it turns out that x squared minus 4x plus 7, that trinomial that is on the bottom of that integral there, can also be written as x minus 2 all squared plus 3. That is sort of the, the completed square version of this trinomial on the bottom. So this integral is equal to, or can be rewritten as, dx with x minus 2 all squared plus 3 on the bottom.
Could we pull that plus 3 out?
You cannot. It is not being So you could do that if this were the situation. If there were just a 3 like being multiplied, or like on the bottom of this fraction as a factor, yeah, you could definitely like take a 1/3 out of the whole thing. But that plus 3 is being added. It is not a factor. It's just part of this whole thing. I guess you could factor out like a 3 if you really wanted, but the way that it would end up looking is like kind of like that. Yeah, you'd have to factor it out every individual term on the bottom. Okay, so this might still look a little foreign, but important thing here is that is a variable term squared plus a constant squared, which identifies this as becoming, when you integrate it, an arctangent. Right, that's the only one. Arctangent is the only function whose derivative involves adding the two things on the bottom. Okay, so now that we know it's sort of in this arctangent thing, the thing that we want to do is we want to identify u and identify a. So this whole squared binomial is u squared. So u squared is x minus 2 all squared, the square root of which would just be x minus 2. And as a formality, we'll say, okay, well, u is not just x, it's x minus 2. Maybe we're going to have to figure out what du is, but the derivative of 2 is nothing, so we don't actually have to do like a u substitution here. Since it otherwise is just x, it's just an extra constant being added, which is ultimately inconsequential. Here a squared is 3, meaning that a is the square root of 3. No u substitution necessary. So we can just start writing this. This antiderivative is going to be 1 over a, right? Because when you integrate into an arctan, there is always a 1 over a in the front. So 1 over that square root of 3 times the arctan of u over a. U being this x minus 2, right? The whole expression x minus 2, that's u, over a, which again is square root of 3. Plus c. Right, so through completing the square, you can take something that looks relatively essentially like nothing you've seen before, right? There's no real form or like known antiderivative that really allows you to integrate like dx over x squared minus 4x plus 7 like immediately. But through completing the square, you can make it look like you can sort of rewrite the expression to where it is more obviously in the form of something that you do know, arctan in this case. So it is so being able to complete the square is important for being able to do these antiderivatives that integrate into being inverse trig functions. Yeah. We'll just look at these real quick, just in case there was anything we missed on the first day. Okay. Sure, you guys are. Sure, we covered most of these. if you already know, you don't have to write any of these down. Particularly if we wrote them down earlier. If there's anything we didn't cover, I guess we could. But this first rule is simply saying if you have a constant on the inside of an integral, you can take the constant to the outside of the integral. Has to be a constant though, like a coefficient, that's being multiplied. You can take that into or out of the integral sign as you want. Taking the integral of a sum or a difference, you can take the individual integrals and then add or subtract them after. The integral of 1. I know this says the integral of du is u. Like, that is true, but you can also think of it as being, as saying the integral of 1 is u. Let's see. Same reason, the derivative of u would be 1, so the integral of 1 would be u. This is simply the power rule, saying that when you integrate, the power rule is add 1 to the power, divided by the new power. So long as n is not a power of negative 1. If it is a power of negative 1, meaning that you're going to have a u on the bottom, well, 1 over u du, or du over u, integrates into the natural log. Integral of e to the u is e to the u. This is simply a special case where you're not, where you're dealing with some base other than e, which is exceedingly rare. And then we're just going to sort of start on the trigonometric integrals, which we also covered. Integral of sine is negative cosine. Integral of cosine is positive sine. I don't know if we necessarily covered this. Tangent of u is the negative natural log of cosine of u. Maybe I'll show you guys these two. We end up having time, which we probably will. But these are just like a lot of these are just the reverse of a lot of derivative rules, and then these last three are the ones that we just learned today. The integrals that have arcsine and arctan and arcsecant as their antiderivatives. So we're not actually gonna I guess we could, but we're gonna look at sort of these three very similar looking integrals, and despite the fact that they look similar, they would be solved in completely different ways. We're just going to sort of look at what makes them different. So this first one has an x. They all have the square root of x squared minus 1. This first one has an extra x on the bottom, and this second one has an extra x on the top. Now, we just sort of learned about this, so you might recognize this first one. An extra x on the bottom, on the outside of a square root, with a x squared minus 1 under the square root, that is an arcsecant. That's an arcsecant with a equal to 1 and u equal to x. So how that's going to integrate is 1 over a, so 1 over 1, times the arcsecant of u over 1, so x over 1, or just, literally just arcsecant of x. Let's see. The second one has x on the top, and so it's not arcsecant anymore. In fact, it might appear at first to be sort of difficult to tell what this is supposed to be. But you might, if you sort of notice that up top you have x dx, and, sort of wedged inside of the bottom underneath that square root is this entire expression x squared minus 1, well, x, a linear factor like x is going to be the derivative of a quadratic factor like x squared minus 1. So you might say, well, let's just sort of see what happens if we allow this x squared minus 1, this function that's inside of this other function, that's technically inside of a third function, is called u. Like, let's see what happens there. So if u is this x squared minus 1, well, then du should be 2x dx. And while you could take this and divide by 2 or divide by 2x, you can totally do either. Both should result in the same thing. I'll try dividing by 2x. I'll try isolating the dx and seeing what happens. But since we have that x up there, this looks like it's going to be like a working u substitution. Okay, don't really know what to do with this x, so I'll just leave it as an x. The dx we can replace with 1 over 2x du, according to this. And on the bottom, the square root of, well, we said this entire thing was u, so we'll just have that there. Okay, well, we got x right next to a 1 over 2x. We can cancel those out right away. And we're just going to be left with a 1/2 du. And we can even take the 1/2, like the resulting 1/2 to the front, right? Those x's have gotten rid of each other on the top, so we just have this 1/2, and we're going to take it, in the front here. So it looks like this is going to be solvable through u substitution. So 1/2 times du over square root of u still looks kind of weird, but if you have a square root of u, you can write it as u to the 1/2. If it's on the bottom, you can write it as u to the negative 1/2. So this is u to the negative 1/2 du. It's just a power of u, right? It's a 1/2 because it's a square root, and it's negative because that square root is on the bottom. But it is just a power of u. Meaning that you can apply the power rule. You're going to add 1 to the power and divide by the new power. There's still this 1/2. But then this integral, where we're going to take u, add 1 to the power. If the power is currently negative 1/2, adding 1 makes that positive 1/2. And we're going to divide by this new power. Okay, well, dividing by 1/2 is the same thing as multiplying by 2, right? Dividing by anything is the same as multiplying by its reciprocal. So this is going to be 1/2 times 2u to the 1/2 plus c. Well, that 1/2 and that 2 are going to cancel out. And so we just have u to the 1/2 plus c, which is, what was u? X squared plus 1, x squared minus 1 to the 1/2 plus c. That is the antiderivative. If you want to write it as a square root, you can say that, oh, this is going to be the square root of x squared minus 1 plus c. But this is fine too. So, just by having an x on the top instead of the bottom, it becomes a u substitution instead of an inverse. inverse trigonometric integrals are completely different, even though it otherwise looks identical. So it's important to sort of notice these patterns, you know, of like, first of all, does it fit a form that you already know? Or, you know, two, you know, does it sort of look like that, does it sort of look like if you took a part of this integral and called it u, that there would be, you know, that u's derivative sort of hanging out, you know, like there was with the second one. And this third one, simply a dx with x squared minus 1, you might think, oh, okay, this kind of looks like an arc sine. But not so. An arc sine would have 1 minus x squared, not x squared minus 1. There's no x on the bottom to, you know, let this be an arc secant. There's no x on the top to allow you to do a u substitution. This last one, there is no way to integrate this with what we know now, not integrable.